All right, I apologize for my tardiness. If you could, please type here in the chat. Today, we're going to be talking about the concept of nodal analysis. Nodal analysis is a very powerful circuit analysis tool that allows us to determine the value of any unknown voltage in a circuit by using Kirchhoff's current law to develop a system of equations that we are going to solve simultaneously. So what I'm going to do is I'm going to give us a circuit that we're going to analyze, and I'm going to walk us through the steps of nodal analysis. Okay. So our first circuit of interest will be this circuit, in which we have a 15 ohm resistor, over which we have a voltage Vx. Then we're going to have a 5 ohm resistor here. A 20 ohm resistor here. We will have a 10 ohm resistor down here. A 2 amp current source here in the middle. And a 0.5 Vx current source down here on the bottom right. And what I would like us to determine is the power supplied by the 2 amp source and the power supplied by our dependent source. All right, so if we were to look at this circuit, this is probably more difficult than anything that we've analyzed to this point in this class. There are no resistor combinations that we can make. There are no source combinations that we can make. Effectively, there is no means by which that we can simplify this circuit. So what we're going to do is apply the nodal analysis technique. And the first step of this nodal analysis technique is simply to identify all of our nodes. So I'm going to use different colors to identify all of our different nodes. We have one here on the left-hand side, one here in the middle, one on the upper right-hand side, and then purple, one here on the bottom. So this circuit contains 4 nodes. Our next step is going to be select a reference or ground node. So what we're really doing in this step is just picking one of these 4 nodes and saying that the voltage at this particular node is known. And we typically give this value 0 volts. We can select any of the nodes as our reference node or as ground, and we will still be able to solve this particular problem. So typically speaking, I choose a node that has the most elements that are connected to. As we can easily see from our drawing, Every one of these nodes has 3 elements that are connected, so they're all equally likely candidates. So just for the sake of simplicity, I'm going to choose the bottommost node to be my reference node, and I indicate that by connecting a ground symbol to that node. So this ground symbol means effectively that we have a known potential of 0 volts at this node. And then our next step is going to be to assign nodal voltages. Okay. So what that means is I'm simply going to give all of our other nodes a name. So for instance, let's call this red node A, this blue node B, and this green node C. And then I'm going to assign nodal voltages by simply saying that there is some voltage VA at node A, some voltage VB at node B, and some voltage VC at node C. I'm going to take a moment here to explain what these nodal voltages represent. Okay, so the voltage VA, the positive polarity terminal is taken at node A, and the negative polarity terminal is taken at our reference node or ground. So our nodal voltage of VA is effectively just a shorthand notation for the voltage drop over our 10 ohm resistor. Similarly, the nodal voltage at node B is simply the voltage with node B at the positive polarity terminal and ground at the negative polarity terminal. So VB is a shorthand notation for the voltage drop across our 2 amp current source. And our nodal voltage node C is the voltage across our dependent current source, like so. And we can express all of the other voltages in this circuit in terms of these nodal voltages. And that's what we're going to do throughout our analysis. Okay? So a nodal voltage is simply the voltage measured at the terminal or the node that's identified minus our reference node, which will always be 0. All right. So let's move along to step number 4. Okay. Step number 4 is an optional step, but I'm choosing to place it here because this is one of the easiest equations to forget to write. And so we're going to call step number 4 express controlling variables in terms of our nodal voltages. So what I mean by a controlling variable is a quantity that controls a dependent source. In this particular circuit, our controlling variable is this voltage Vx, which is defined to have the positive polarity terminal on the right-hand side and the negative polarity terminal on the left-hand side. So we are going to write an equation that simply says Vx is equal to the nodal voltage that's associated with the positive polarity terminal, which is Vc, minus the nodal voltage which is associated with the negative polarity terminal, which is Va. So we have an expression Vx is equal to Vc minus Va. This is our first equation in our system that we will be solving. Okay. Our next step will be to perform Kirchhoff's current law at each non-reference node. So our circuit contains three non-reference nodes, node A, node B, and node C. And we are going to perform KCL at each of these nodes. So I'm just going to write here, KCL at node A. And I'm going to indicate on our figure which which currents I'm adding together. So we're going to be using formulation number 3 of Kirchhoff's current law. So I'm going to add all of these currents that are leaving node A together. One directed up through our 15 ohm resistor, one directed right through our 5 ohm resistor, and one directed down through our 10 ohm resistor. And I'm going to express these currents in terms of my nodal voltages using simply Ohm's law, okay? So for instance, the current flowing through the 15 ohm resistor, I'm going to express that as VA minus VC over 15 ohms. So what I've done here is I've said the node where my current starts from minus the node that my current flows to divided by the resistor value, okay? I'm going to do something similar here for the current flowing through the 5 ohm resistor. So the current flowing through the 5 ohm resistor is going to look like VA minus VB divided by 5 ohms. And finally, we're going to have the current flowing down. So the current starts at node A. So we're going to have plus VA. It ends or flows into our reference node, which has a voltage of 0. So I'm going to have VA minus 0, or just VA, over 10 ohms. And since there are only 3 currents flowing out of node A, I've identified all of them, expressed them in terms of my nodal voltages, so I'm ready to set this KCL equation equal to 0. And then I repeat this process for nodes B and C. So I'm going to scroll back up here. Let's use pink for this one. So I have a current flowing to the left out of node B. I have a current flowing down out of node B, and I have a current flowing to the right out of node B. Would anybody be willing to volunteer in helping me write our equation for this node? All right, sounds like the answer to that question regarding volunteers is a resounding no, so I guess I'll write it for you. So let's start with the current directed to the left through the 5 ohm resistor. The current starts at node B and flows into node A. So we're going to have VB minus VA over 5 ohms. Then we have a current flowing down. So we see that the current in the pink flowing down is opposite the direction of our 2 amp source. So that means we're going to have minus 2 amps. And then we have our current flowing to the right through the 20 ohm resistor. This current starts at node B and flows into node C. So we're going to have VB minus VC over 20 ohms. And we're going to set this equal to 0. And now we're ready to write our KCL equation for node C. So let's scroll back up here, and I'm just going to identify my currents. So I have one flowing to the left through the 20 ohm resistor, one flowing up through the 15 ohm resistor, and one flowing down through my dependent source. So let's start with the one flowing up. That's going to be VC minus VA over 15 ohms. We have our current flowing to the left. So that's going to be VC minus VB over 20 ohms. And then finally, we have our current flowing down. Since this current in orange flowing down is in the same direction as our dependent current source, we're going to have positive 0.5 Vx. And set this equal to 0. And we now have 1, 2, 3, 4 equations and 4 unknowns. And so we are at a point where some of us can actually throw this system into our calculators. So I'd like to talk for a brief moment here about the calculator options for this class, because I don't think I've done it to this point, okay? On your exams and things like that, you're expected to be using an NCEES approved calculator, much like you used on your engineering 120 series exams, and like you've used on your engineering 220 and 222 exams for those of you who have taken statics and thermo, okay? There are some subtle differences between these calculators. For instance, the TI-36X, which is one of my personal favorite calculators. I know I'm a big dork for having a favorite calculator. It is a very good calculator to use for complex algebra, which is something that we're going to be doing quite a lot of later on in this class. The TI-36X is capable of solving a system of equations that contains 3 equations and 3 unknowns, meaning that we would have to make some sort of simplification here in order to use a TI-36X to do it. And I'll detail what that simplification is in a moment. The Casio FX115 is also only capable of solving a 3 equation, 3 unknown system. The Casio 991, however, is capable of solving a 4 equation, 4 unknown system. So it's actually my preferred calculator to use at this portion of the class, because it's got a little bit more processing power. And so I don't have to make as many simplifications in order to solve my circuits. If you prefer a different type of calculator, there's nothing preventing you or I from continuing to use that one. But if you're looking for an upgrade for a calculator and you've got roughly $20 to spare, I think the Casio 991 is a pretty good purchase for this class, just because it's a little bit more powerful and will make this class a small amount more easy for you. But let's assume that you don't have the fancy calculator that I suggested, and we need to get this down into a 3 equation, 3 unknown system, which all of the NCEES approved calculators should be able to handle. We can do that by simply substituting equation 1 into equation 4, right? We know that 0.5 Vx can be expressed in terms of our nodal voltages. And so what we're going to wind up having, if we substitute in here, Vx is equal to Vc minus Va, is a system of equations. And I am going to write this system down in a matrix form. We're not actually going to use the matrix per se, but this is how we're going to enter things into our calculators. Okay. So I'm going to have to go to my next page, apparently, in order to give us our matrix. So we're going to have some coefficient. So I'm going to call this C1. And this is our coefficient for our first variable in each of our three equations. Then we're going to have some second coefficient, which I'm going to call C2, and some third coefficient, C3, that'll be in our coefficient matrix. This coefficient matrix is then multiplied by our variable vector here, which in this case is going to be the voltage VA, VB, and VC. And this will equal a vector of constant terms, which I'm going to call K. Okay, so let's scroll back to the previous page and look at our equation 2, our first KCL equation. Okay, so the coefficient of VA is going to be 1/15 coming from our first term, plus 1/5 coming from our second term, plus 1/10 coming from our third term. So I'm going to go back to my matrix. I'm just going to write those down. 1/15 plus 1/5 plus 1/10. I'm going to go back to that first KCL equation, and I can see that my coefficient for VB is -1/5, and that's the only VB I see in that equation. So I'm going to put a -1/5 here. And if I go back in my first equation, I have a coefficient of -1/15 for VC, and that's the only VC I see. So -1/15 will go here. And finally, I'm going to check to see if I have any constant terms. And I do not have any constant terms that needed to be moved to the right-hand side of my equal sign. So my constant term in my first expression is going to be 0. Now let's look at our second KCL equation. So in my second KCL equation, I see that VA has a coefficient of -1/5. My coefficient for VB is +1/5 plus 1/20. My coefficient for VC is -1/20. And I am going to have a constant term. Sorry, let me scroll down here. So I'm moving this 2 amps to the right-hand side of the equal sign. So it's going to look like +2. And now I'm ready for my third KCL equation. So I have a coefficient of -1/15 from this first term. And then I'm also going to have a coefficient of -0.5 from this third term. So that's -1/15 minus 1/2. For VB, I only have a -1/20. For VC, I have 1/15 plus 1/20 plus 1/2 for my VX term. So 1/15 plus 1/20 plus 0.5. And just double checking, I believe my constant term is 0, but I just want to make sure. Yes, I don't see any constant terms here. So we would put a 0 here. And then we can throw this system into our calculator or a computer algebra tool or use Kramer's rule or however we feel like solving this 3-equation, 3-unknown system, okay? I believe at this point, you guys have likely had to solve system of equations in your Engineering 120 series. You have been introduced to MathCAD to solve systems of equations. You've learned a couple of other ways using your pre-calculus classes. Whatever method best suits you is okay by me, but obviously for your exams, the expectation is that you wouldn't be able to use a computer algebra tool like MathCAD. So you should probably get some practice using your calculator to do it. All right, so if you enter in this coefficient matrix into your calculator, as well as your constant term matrix into your calculator, and solve this system, what you will find when you solve this system simultaneously is that the voltage VA comes out to be about 16.7 volts. The voltage VB comes out to be about 24.8 volts. And the voltage VC comes out to be about 17.4 volts. Now that we know these 3 nodal voltages, we could figure out any other voltage that we wanted in the circuit. So for instance, we know that Vx is equal to Vc minus Va, which would be simply 17.4 minus 16.7, or 0.7 volts. We could determine the voltage drop over the 5 ohm resistor by saying either VA minus VB if we wanted the positive polarity terminal to be on the left, or VB minus VA if we wanted the positive polarity terminal to be on the right. So since we're trying to figure out the power supplied by these sources, what I'm going to do here is I'm going to erase some of these things, these arrows that we use to write our KCL equations, and we're going to figure out what polarities we need our voltages to be across these current source in order to determine supplied power, okay? So for our 2 amp source, and since we're calculating supplied power, what we're looking for is a voltage having this polarity. So I'm going to call this V 2 amps. And for our dependent source, again, we're calculating supplied power. So I want the current flowing into the negative polarity terminal. So we're going to call this voltage V dependent. Well, how can we express that voltage V 2 amps or that voltage V dependent in terms of the nodal voltages that we've already solved for? Well, V 2 amps is going to be the voltage, the nodal voltage associated with the positive polarity terminal, which is VB, minus the nodal voltage which is associated with the negative polarity terminal, or 0 volts. So the voltage drop across the 2 amp source is simply VB. The voltage that I've labeled as V dependent will be the voltage associated with the positive polarity terminal, which is 0 volts, minus the voltage that I've associated with the negative polarity terminal, which is VC. So V dependent is simply negative VC. And from here, we could determine our powers simply saying the current 2 amps times our voltage VB. Let's look down at what that was. 24.8 volts is the power supplied by our 2 amp source. comes out to be 49.6 watts. For our dependent source, our current is 0.5 times Vx, which we found to be 0.7 volts, times negative Vc, where negative Vc is negative 17.4 volts. And so we get negative 6.09 watts of supply power. So this nodal analysis tool, as I've illustrated it, is very powerful. We found we now have a means by which to determine every voltage in this circuit. Once we know those nodal voltages, we can use Ohm's law to determine any unknown currents, and we can then use those relationships combined to figure out any unknown amount of power in our circuit. So nodal analysis provides us enough information within a step or two after completing it to determine literally any quantity that I could ask you for any given circuit. Does anybody have any questions thus far? All right. So what we're going to do now is we're going to analyze a circuit that contains a voltage source, because as you will notice, in this particular circuit, I only included current sources. Voltage sources are a little bit tricky, and I'll explain why. Okay. So let's look at the following circuit. We have a 4 ohm resistor here. Two ohm resistor here. Let's put a dependent voltage source on top. Put a 6 ohm resistor here. Diagonally across, give ourselves a 3 ohm resistor. Put an 8 ohm resistor over here. Let's do a 0.4 amp source here. Short circuit across here. A 10 ohm resistor here. A 15 volt source here. A dependent current source carrying 2 IX. A 9 volt source here. And a 5 ohm resistor here. So this is the circuit that we are going to try to analyze, and our ultimate goal in this one will simply be to determine the current IX, where I'm going to define IX to be the current flowing to the right through our 10 ohm resistor. So my first step in employing the nodal analysis technique is to identify my nodes. So I'm going to take a moment to do that. We have this guy on the top right, excuse me, top left. This node on the top right. This node on the middle left. This node in the middle. This node on the middle right. And this node on the bottom. Okay. So I want you guys to help steer this analysis. So I would like, we've identified our nodes. I would like for one of you to just tell me a color that our reference node is going to be. So by my count, there are 14 of you, literally one of you, 14 people, type a color into chat that I've used. Purple. Thank you, Sean. All right, so we're going to choose this node here in the middle to be our reference node. So our next step is going to be to assign our nodal voltages. Okay. So I'm going to say that my red node has a nodal voltage of VA, my blue node VB, my green node VC, my pink node VD, and my teal node, or turquoise or whatever color that is, VE. All right. Step number 4 will be the same. That is going to be to express our controlling variables in terms of our nodal voltages. So in this instance, our controlling variable is this current IX directed to the right. And so I am going to say that IX is equal to the nodal voltage that our current starts from, which is our reference node. So we're going to have 0 minus the node that our current is flowing into. So that's 0 minus VD divided by our resistor value of 10 ohms. And so we can say that IX is simply negative VD over 10 ohms. All right. So that's our first equation. There is going to be a new step 5, but I'm going to come back to this step after I've explained effectively why we need it. Okay. So instead, I'm going to give myself some room here, and we're going to move along to step 6. oops, I don't need to write step 6 because I've already got 6 with the circle in it, which is going to be to apply KCL at non-reference nodes. And we're going to modify this step very slightly in just a moment. And we'll see why here, okay? So let's start at node A. So at node A, I'm going to be adding the following currents together, right? So we have this current flowing down that's leaving node A, this current flowing down that's leaving node A, this current flowing diagonally to the right that's leaving node A, and this current flowing to the right through our dependent source that's leaving node A. So let's start with our current flowing down through our 4 ohm resistor. That's going to be VA minus VC over 4 ohms. Now let's look at the current flowing down through our 2 ohm resistor. That's going to be VA minus 0 over 2 ohms. Now we'll have the current flowing diagonally down through the 3 ohm resistor, which is going to look like VA minus 0 over 3 ohms. And now we're going to have the current that's flowing through our dependent source. And we run into a little bit of a problem here, okay? So the problem that we are facing is that we are trying to express the current that is flowing through a voltage source in terms of our nodal voltages. And the problem that we have is that the current that's flowing through a voltage source is entirely independent of the voltage that's being provided by the source, okay? We don't have any real means by which to express this current that's flowing to the right through our dependent source in terms of our nodal voltages. So what I'm going to do is I'm just going to call this current, for lack of a better thing, I dependent LR, because it's flowing through the dependent source from left to right. I'm going to add all these currents together and set them equal to 0. We're just going to have to figure out what to do with that current in a little bit. Now let's write our KCL expression at node B. So we're going to have this current directed to the left, this current directed down, and this current directed down. If we start with the one directed to the left, we run into the exact same problem that we just saw a moment ago. We're trying to express the current that's flowing through a voltage source in terms of our nodal voltages, and we literally cannot do it. So instead, I'm going to call this I dependent RL, because it's the current that's flowing from right to left through our dependent source. Then I'm going to have the current flowing down through the 6 ohm resistor, which is simply VB over 6 ohms. Then I'm going to have the current that's flowing down through my 8 ohm resistor, which is VB minus VD over 8 ohms. and set this all equal to 0. So we're going to pause here for a moment and make an observation. Okay. Our KCL equation at node A contains the current that's flowing through my dependent source from left to right. And my KCL equation at node B contains the current that's flowing through my dependent source from right to left. These two currents have to be identical, and they have to have opposite signs because they represent the same current flowing in opposite directions. Okay. So what we are going to do is we're going to add these KCL equations together, because that's going to cause those two currents, I dependent left to right and I dependent right to left, to cancel each other out. Okay. We can do this because the KCL equation at node A is equal to 0, and the KCL equation at node B is equal to 0, and 0 plus 0 has to be equal to 0. We're going to treat this phenomenon effectively as what I'm going to call a supernode. Okay. So instead of writing individual KCL equations, what we're going to do is we're going to, let me erase these guys right here. Lump these two nodes together, and we're going to sum all of the currents that are leaving our supernode. Okay, and that's what our real step 6 is. So I'm going to modify this right here to say non-reference supernodes. And I'm going to leave these guys right here so that we can see what happens. Okay, so KCL at supernode A, B, because it contains nodes A and B, our equation is going to be the current flowing down through our 4 ohm resistor, which is VA minus VC over 4 ohms. So we've included this guy. The current flowing down through our 2 ohm resistor, which is VA over 2 ohms. So we've included this guy. The current flowing diagonally down through the 3 ohm resistor, which is going to be VA over 3 ohms. So we've taken care of this guy. Then we see a current flowing down through the 6 ohm resistor that's leaving our supernode. So that's going to be VB over 6 ohms. And then we have the current that's flowing down through the 8 ohm resistor that's leaving our supernode. So that's going to be VB minus VD over 8 ohms. And set this equal to 0. Okay. So just to be clear here, we included this guy, and we included this guy. The reason we didn't include this and didn't include this in our supernode equation is because those two currents cancel each other out. If we added this guy and this guy together, we would get this equation. Okay. So I want to scroll back up here. Anytime we have a voltage source, we are going to have a supernode. So I'm going to identify my other supernodes in this circuit. I have a supernode here containing nodes C and E. And then in a different color, I'm going to circle this other supernode. I'll do this in light purple. And I'm doing this one in a different color because this one in light purple is special. The reason why I say that this supernode that I've circled in light purple is special is because this supernode contains our reference node, right? This is a supernode between nodes E and our ground node. Because we only write KCL equations for our non-reference nodes, that means we will not write a KCL equation for this particular supernode. And the reason why we don't have to goes back to that equation 5, or excuse me, step 5 that I skipped, okay? So let's talk about step 5 now. When we wrote our KCL equation for supernode AB, that supernode contains 2 nodes, so we need to be able to get 2 equations out of it. Our first equation is our KCL equation. Our second equation is going to be a voltage relationship equation. And we are going to have to write a voltage relationship equation for all voltage sources. So let's start with something simple. Our 15-volt source, okay? Our voltage relationship equation for our 15-volt source is simply going to be the nodal voltage associated with the positive polarity terminal, which is VC, minus the nodal voltage that's associated with the negative polarity terminal, which is VE. So our first voltage relationship equation is simply 15 volts is VC minus VE. Now, let's look at our 9-volt source. The voltage that's associated with the positive polarity terminal is ground, or 0. So we're going to have 0 minus the voltage that's associated with the negative polarity terminal, which is VE. So we can say that 9 volts is equal to negative VE. And lastly, let's look at our dependent source. So we have 5Ix is equal to the voltage that's associated with the positive polarity terminal, VA, minus the voltage that's associated with the negative polarity terminal, VB. So those are our voltage relationship equations. Now, let's just look at things here real quick. We have, let's do these in blue. 1 equation, 2 equations, 3 equations, 4 equations. Here is our 5th equation. We still have a few more to write. We have our 5 nodal voltages, VA through VB. And then we also have, VA through VE. And then we also have our controlling variable current IX. So we have 6 total equations that we should need to write here. All right. So what would happen if we tried to write a KCL equation for supernode CE. Let's see what happens here, okay? So I'm going to scroll back up and I'm going to identify the currents that are leaving supernode CE. Let's do this in this gray. Okay. So we have this current flowing up that's leaving node C, this current that's flowing to the right that's leaving node C, this current that's flowing up that's leaving our dependent current source, this current that's flowing up through our 5 ohm resistor, and then, this current that's flowing up through our 9 volt source. So we have a problem here because we are trying to express the current that's flowing through our voltage source again, okay? So what happens when we have 2 voltage sources that are touching each other is that we form a super duper node. And this super duper node, which is simply the bubble that I've outlined in orange combined with the bubble that I've outlined in light purple, since this contains the reference node, we don't actually have to write a KCL equation for this either, okay? So anytime we have voltage sources that are connected and one of them is touching our reference, we don't have to write a KCL equation. Our last equation that we need, because we have identified that we have 6 variables and we've written 5 equations, will come from writing a KCL equation at this normal node, node D, okay? So our last step here, I'm just gonna scratch this out because we don't have to do it. So our last step, step 7, will be to write KCL equation for any remaining non-reference nodes, which in this case, the only remaining non-reference node was node D. And let's look back here. So we're going to have a current flowing up, VD minus VB over 8 ohms. We're going to have a current flowing to the left, which is going to be VD minus 0 over 10 ohms. And we're going to have a current flowing down. Sorry, I went the wrong direction. The current flowing down is going to be VD minus VE over 5 ohms. And set this equal to 0, okay? Here is our 6th equation. We have 6 equations, 6 unknowns. This is obviously more than we could possibly put into any of our calculators. So we would have to use MathCAD to analyze this particular circuit. So my question to you guys is then, do you need a refresher on using MathCAD for solving systems of equations? All right, so the only person that responded was Mr. Smith, and he said that he does not need a refresher. No one else is responding, so I will assume that you are all comfortable using MathCAD to solve system of equations. If you happen to change your mind, I'll be lurking here on Zoom, and I'm also available to look at your MathCAD sheets if you send them to me via email or anything like that, okay? So at this point, our nodal analysis procedure is done, and we're simply solving our systems, which ostensibly you guys know how to do. So I'm done with my lecture for today. If you have any questions, like I said, I'll be here on Zoom to answer them. If not, I hope you have a great weekend, and I will see you on Monday afternoon.